السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. This is Engineer Khalil Masaid. I will introduce in this video the Instrumentation Engineering 232, the final control element, which is in Chapter 7. Mr. Yamin Qadri, he has explained to you also from the same chapter the actuators and different type of actuators. I will continue with the final control elements. So the function of the final control element is to translate low energy control signal into a level of action commensurate with the pressure under control. We have this diagram. This is the control signal comes from the controller, which is maybe a current like 4 to 20 milliampere, or voltage, or a pneumatic signal. We have a signal converter here. So the first block here is the signal conversion. This device performs signal conversions and is often called transducer. So it is type transducer or transducers, because they convert control signals from one form to another, such as current to pressure, current to voltage, or current to voltage, yes, or current or pressure to current, etc. Then we have, so this is the signal conversion. It is a converter or transducer. Then we have the actuator. This is the actuator. As Mr. Yamin already explained to you, the actuator is translation of the converted control signal into action on the control element. So this actuator, depending on the signal coming from the converter, it will make or create or generate an action. And usually, in most of the cases, the action is a type of mechanical action. Like the linear movement or rotational movement. Linear movement, either push or pull. Rotational movement, either clockwise or anti-clockwise. Okay. Then we have the final control element. The final control element, or the control element, is run by the actuator. So the actuator apply force, maybe mechanical force, as I said, to the final control element. The final control element will affect the process, either increasing in temperature, increasing the speed, increasing the pressure, the flow, etc. So the final control element here will affect one or more physical quantity of the process itself. The process is operation under control. For example, if we have a furnace, we need to control its temperature. Then we have fuel. So the flow of fuel to the furnace will be maybe increased to increase the temperature, or decrease to decrease the temperature. So by controlling the flow of fuel, we control the temperature. So in this case, we have a final control element to control the flow of the process. We have an example here. This is an oven here. We have crackers here. So the crackers move with the conveyor belt here. We have, this is the supply of crackers here. Okay, before the oven, for entering the oven. Then after entering the oven, there is a sensor here, photocell, a light source with a photocell to see if the cracker is baked well. And there is a signal conditioning here to convert the signal of the sensor, and it gives a current from 4 to 20 milliampere as a feedback signal to the controller. So actually this is a PV value, process variable, as a feedback signal, and we have the set point here. So again, the controller here is comparing between the set point, which is SP or SV, and the PV value, and generate a signal from 4 to 20 milliamps also, because it is standard. And this is usually is called MV value, manipulated variable or value out of the controller. And here this is the converter that converts the signal to voltage, and this voltage will change the speed of the conveyor motor. The conveyor motor here actually is here in this case, in our example here, is the actuator. It is a type of actuator. So we have this actuator here. Okay, and this actuator, while we change the speed of the actuator here, we change the speed of the conveyor belt. So the final control element here is the conveyor system. This is the final control element. This is the final control element. Okay, this is the final control element. So you can see here from this example, all the components here are connected to each other, and they are interacted with each other to have control on the product itself, which is in this case the crackers. Okay. Now let's start with the types of different types of final control. We have mechanical, we have electrical, and we have fluid. So let's start with the mechanical control elements. The mechanical control element, we have an example on this, which is the solid material hopper valves. So this is a hopper here with a grain bin. This is the grain bin, okay, filled with the grains. And this is the hopper valve, and this is the conveyor belt. We have a sensor here to measure the flow of grains depending on the thickness. If the thickness here is large, then the flow is large. If the thickness is low, then the flow is low. So this gives a signal here to the controller as a PV value in terms of current, for example. And this is the SB value. The controller will compare between these two values and initiate a signal, which is the manipulated variable. This is the MV, goes to the actuator. The actuator here is usually mechanical, or sorry, maybe mechanical or electrical, or maybe pneumatic or hydraulic. So we have piston here. This piston push the gate of the hopper valve to close it, or pull the gate to open it. So this actuator may be a pneumatic cylinder or hydraulic cylinder, or just a motor with linear motion, linear motor. This is the actuator here. This is our actuator here, and here we have the final control element. In this case, the final control element is the hopper valve. This is the final control element. Final control. Okay. This is the final control. Okay, and we have a closed loop in this case. Another example of mechanical control, final control, is the paper thickness control. This is the paper thickness control. We have continuous feed of wet fiber here, goes between two rollers, one movable roller, this is a movable roller, and here we have fixed roller. The two rollers here, this is the worm screw motor here, apply force to the movable roller to force it down to decrease the thickness, or move it up, reduce the force to reduce the force, yes, to increase the thickness. If the force go down, then we decrease the thickness. If the force go up, the thickness will be increased. And this has a sensor here, an LVDT sensor that measures the thickness, and here the signal conversion, convert the signal, and we have the converter. This is the set point value, and we have, this is the B value, and we have here the MV value, and this is the signal converter, and this is the actuator. Our actuator, in this case, this worm screw, this is the actuator. This is our actuator, and it is a motor, a type of motor with linear motion. And we have the movable roller here is the final control. This is the final control in this case. This is the final control. So in general, every control loop, I mean continuous control loop, that will incorporate a controller, signal conversions. In this case, we have two signal converters. Sometimes we need only one conversion. We need a sensor, we need the actuator, we need a final control element, okay, and the process itself. Okay. Then we have electrical final control element. One example is this. We have a motor. We need to control the speed, so it is a motor speed control. We need to control the speed of this shaft. In this case, we have a tacho generator here that sends the speed of the motor and gives a voltage. Voltage here, for example, we have from 0 to 10 volt as an example. It depends on the speed, and this is our BV value, and this is our set point reference speed, and the controller will compare these two, the set point and BV value, and initiate a manipulated variable NV to the actuator. This is our actuator in this case. This is our actuator. Okay, and the brushes, the brushes here, our actuator. The motor itself is the final control element. These are fields are required for DC motor, because this is a DC motor. Okay, DC motor. So the motor itself is the final element or final control element. Sorry, mouse is not helping. So in this case, the motor is used as a final control element. Some other cases, the motor is used as an actuator, because it need, when we need a rotation, the shaft rotating to open a valve, to close a valve. In this case, the motor is an actuator. Okay. We have another example of electrical final control element. In this case, we have a temperature control. We have this temperature sensor, and we have temperature measurement here. We have the controller, we have the set point here. We have the BV value here. We have MV value here. Okay, and we have this power amplifier. The power amplifier here will amplify the signal, okay, to give large current to the heating coils. So this is our actuator here in this case, an electrical actuator. Okay. And the heating coil in this case is the final control element. This is the final control element. Okay. And it is electrical because the coil usually is a type of resistance. When you apply current, pass current through the coil, the resistance will dissipate heat proportional to I squared R, and this heat actually influence the temperature in the reaction vessel, this reaction vessel. Okay, so if we increase the heat, increase the current here, increase the heat, then we increase the temperature. If we reduce the current, reduce the heat, then we reduce the temperature. Okay, so all the components are there here also. Now we have the third type of final control element, which is the fluid valves. And one of the most important and well common in the industry of fluid valves is the control valve. This is the control valve, and it consists actually from the stem here. This is the stem that goes up and down. And we have the plug. This plug is fitted at the top, the head of the stem here. And we have the seat here. This is the seat. So when we apply or when the stem goes down, so it pushes the plug down to the seat. And if the plug is fully seated, then the control valve will be fully closed, 100% closed. Okay. And if the stem goes up, then it will the plug will go up also, and will open the valve. So this is the pipe here. This is the flow in. This is the flow out. Okay. And actually, the control valve operate as a final control element. It needs an actuator, and the most common actuator is the pneumatic actuator. This type of actuator. We apply the current here comes from the controller as 4 to 20 milliamps standard. Okay, standard industry standard. And this current, we have this converter, I to B converter, convert the current to pressure from 3 to 15 psi. Okay, sorry here. And the pressure applied here. Okay, we have this pressure will generate force depending on the area of this head here, because you know the pressure is equal to force divided by area. The area here is the diaphragm area. This diaphragm fitted from between 2 points, this point and this point. This is the diaphragm. This is our the diaphragm here. Okay, and we have the spring here. We have the stem here. This is the stem. Okay, and this is the seat, and we have this is the plug. Okay, so if we know the area of the diaphragm, and we know the pressure, because the pressure ranges from 3 to from 3 to 15 psi, we can calculate the force. This force is applied here to push down the stem and the plug toward the seat. So because we have a range from 3 to 15 psi, corresponding to a range of current from 4 to 20 milliamps, then we can control the opening of the control valve from 0 to 100%. This is called control valve because we can control the opening, the stem position. At any point, the stem can be controlled from 0 to 100%. So it can fully open, fully close, or half, 20%, 60%, any value. It is a proportional valve, not like on-off valve. On-off valve only either open, fully open, or fully closed. And we have, okay, this is the valve body, and in this case, in this example, this diagram, this control valve is normally open valve. Normally open valve, because we apply the pressure from the top here to close it. So it is normally open. When apply pressure, then we will close it. So it is normally open. Okay. So, or we can call it in other words, it is called air to open. We apply air pressure to close. Sorry. The same meaning. Air to close means it is normally open. If the pressure applied from the bottom, from here, not from the top, like another actuator type, then we have normally closed. So we apply pressure from here to raise this stem in the upper position, to the upper position, okay, to open the valve. So in this case, it is normally closed. If it is from down, it is normally closed. If it is from the top here, like this one, it is normally open. So we have air to close or air to open. Okay, so these have the same meaning. Okay. The control valve itself, we have the characteristic of the control valve can be classified in 3 types. The first type is the quick opening one, which is this one. Okay, and this type here, this curve, the x-axis here is the stem position, which is normalized as S over S max. This is the stem position divided by the stem maximum position. And the maximum is 1 correspond to 100%, and the minimum is 0. This is 20%, this is 40%, this is 60%, and this is 80%. And the y-axis here is the flow rate, and it is normalized also as Q divided by Q max. The maximum is 1, which is 100%, and the minimum is here in this case. The scale is here 0, but the minimum here, yes, the scale is 0, and here it is 0. For the quick opening, only a very small amount, like 10% at this point, for example, you can see this one, is enough to make the valve 80% open. If it is normally closed, if it is closed, just apply, make the stem move only 10%, only this value. It will make 8, so it is a quick open, very quick open, 80% by only 10%. So this one can be used like on-off control valve, like on-off valve in the case of emergency shutdown system, etc. Okay. The other type is the linear control valve, which is this, and this one is you see it is a straight line, and the slope here is 1. The slope is 1 because the distance here is the same as the distance here. When you divide this, this is from 0 to 1, and this is from 0 to 1. So 1 by 1, it is 1, the slope. So when you increase the percentage, the stem position from 20 to 40, the flow will change from 20 to 40 also. Okay. If you increase the stem from 40% to 60%, then you have an increase from in flow also from 40 to 60. So for linear, we can say for linear, this is for linear, we can say Q over Q max, which is the y-axis, is equal to S over S max, which is the x-axis. Okay, because the slope is 1. This is for linear. Now the third type, which is very important, which is it is the equal percentage. This is equal percentage. Okay, this is very important type because most common used in control applications. Okay, so we can control the opening very easy in this type. And it is an exponential. It has an exponential characteristic or logarithmic characteristic. And when the stem at 0, the flow will not be 0 in this type. It will be start from Q minimum. And in this case, Q minimum, we can calculate it because the most important factor in this equal percentage value is the R, the value of R, which is rangeability. In this case, it is equal to 30. Rangeability. What is rangeability? Rangeability okay, R is equal to Q max over Q minimum. And using this curve, Q max is 1 divided by Q minimum, which is around 0.03. From where I get this number? Because we have 30. When we divide 1 by x, this is unknown, we should have 30. So I found this value. I calculate this value because I know that R is 30. Okay. And we have the formula for equal percentage. Q is equal to Q minimum times R to the power S over S max. For this curve, this example, we have R is 30 and Q minimum is 0.033. So when you multiply 0.033, this value, by 30 to the power 0, when S is 0 here. So anything to the power 0, it is 1. So 1 times 0.033, it will equal to 0.33. So this 0, then this will be 0.033. Now, if S is maximum, so S maximum is if S is equal to S max, so S max over S max, it is 1. So 30 to the power 1, it is 30 times 0.033, it will equal 1. Okay, so this curve, this formula describes this full curve, and it is exponential. Okay, and we can calculate at any point when you start from 40, for example, you have this point. Okay, at 40, and at 60, you have this point. So when you go from 40% to 60%, increasing increase it in 20%, then you have this value, which is around 15%, and this value is around to 25%. Okay, or this is less than, actually, this is less than maybe 12%, and this is 25%. Okay, actually, this one is, I calculated, this is like 13%. This is correspond here to 13%. I calculated using the same equation. This one is 13%. At 60, it is around 25.6. So if you increase the stem from 40 to 60, you increase the flow from 13 to 25.6, say 26. So you double the percent. You double the percent. Now if you increase it from 60 to 80, the same change here. You increase by 20%. Here also you increase by 20%. We expect, because it is equal percentage, then this will equal to 50%. You see, this is 50%. You see this one. This is 50% here. Okay, this is 50%. This is 50%, means double. Here we have 13%, we have around 26, so we double the percentage here. And when you go further by another 20% here, you will get another, you have double also. 25, you have 50. And when you go from 80% to 100% with the same change also, same change, equal percentage, means equal percentage, 20%, 20%, 20%, you have the same effect. You have double from 50 to 100. This is 100. At this point, this is 100 at this point. And this is 50%. So each time you go by 20 here, here you double. So this is the equal percentage. But this is the behavior because we have R30. But if you change R to another value, you will see maybe not double, maybe 3 times or 4 times. It depends on R. R is very important factor, this rangeability. Okay. We will stop at this point. Okay. And we can maybe we'll continue another. But this is the final lecture. We can maybe if we have time we can you can go by the time being to solve examples about regarding this rangeability and the flow, how to find the flow at any point. This formula you can use it to find the flow at any stem position. Okay, for quick, this is for quick percentage. For linear, it is this. The quick opening, we don't have formula for this, but it is usually only the behavior of this we have to know. Okay, we will stop at this point. Thank you very much, and inshallah, I wish you good success. Okay, thank you very much.